continuity is great to review with rational functions. So let's take a look at these rational functions. For each function, we're going to identify the wholes, the intercepts, the horizontal asymptote, which is also known as your end behavior asymptote, domain and range, limit behavior at all vertical asymptotes. So we'll need to write that as a limit, and then we will also sketch our graph. First, I'm going to start off by factoring, by trying to reduce this. Okay, this factors, you have a GCF of x squared minus, and then in the bottom you have a GCF of 4. That continues to factor. You have 4 and 2, both are negative to give you negative 6. For f of x, your reduced version is this right here. Okay, anything that was able to reduce to 1 is in fact a whole, anything that makes that 0. So your whole is going to be at x equals positive 2. You're only given the x value. You do not know the y value of the whole until you know y values on either side of it so that you know an estimate. Intercepts. X-intercepts are the zeros of the numerator. So anything that makes the numerator 0, that would be 0 and 4. These are my x-intercepts. My y-intercept, oh, I already found it. It's 0, 0. Intercepts should always be written as an x, y point. I'm going to write in the vertical asymptotes, but what they're asking for is the limit behavior, so I'll have to write that as well later. So the vertical asymptotes are whatever makes the denominator equal to 0. That would be positive 3. So x equals 3 is your vertical asymptote. Horizontal asymptote is dependent on the degree of the numerator and the degree of the denominator. The degree of the numerator is 3. The degree of the denominator is 2. If the degree is greater in the numerator than in the denominator, you have no horizontal asymptote. If it's less than the degree in the denominator, then your horizontal asymptote is 0. If the degrees are the same, you take the leading coefficient over the leading coefficient of the numerator and denominator to get your horizontal asymptote. Here we have none. The domain here is x is a member of the set of all real numbers, but x cannot equal your wholes or your asymptotes, your vertical asymptotes. I've also written it in interval notation for you. We do need to know what is happening as we are approaching this vertical asymptote and what is happening as our end behavior, okay, as we leave toward infinity and negative infinity. Okay, so to get a better picture, I'm going to plug in negative 1, 1, and 5. And you can plug it into the reduced version. So f of negative 1, the reduced version, would be negative 1 times negative 1 minus 4 over 4 times negative 1 minus 3. That gives us negative 5 over 16. When we do it, when we plug in positive 1, negative 3 over 8, negative 3 over negative 8, which is 3 over 8. And when I plugged in 5, I got out 5/8. I'm going to plot these 3 points on my graph now. Okay, the left side is pretty clear because there's no other way to go through these 3 points. You cannot come back down, right? That would be another x-intercept. So this is curving like this. Okay, we just need to know what's happening here. I'm assuming that it's going to go down this way, but let's test 3.5. This gives me negative 7 over 8. So yes, it does go down like we predicted. Now we know which direction this curve is going in. Now that we know what's happening basically to the left of 2 and the right of 2, we can finally put in our hole. I usually like to do a little bit of erasing and then just put the hole in right wherever the curve shows you that that hole is. They've also asked for the limit behavior at all vertical asymptotes. So we only have one vertical asymptote at x equals 3. And what is happening is that the limit as x approaches 3 from the left of the function we started with, so f of x, is, what is that approaching? As we approach from the left, we're getting higher and higher and higher. We're going towards infinity. The limit as x approaches 3 from the right, as we come from the right toward 3, we get lower and lower and lower. That is going to approach negative infinity. So this is the reduced version, really nothing reduced out of it, but factoring will help us find our vertical asymptotes. So first of all, there are no holes because nothing reduced. It's when you cross things off and to equal 1 that you get holes. Then our vertical asymptotes are anything that makes the denominator equal to 0. Vertical asymptote would be -2 and +2. X-intercepts occur when the numerator is equal to 0, but there's literally nothing you could put in the numerator to make it equal to 0 because there's no variable there. So you have absolutely no x-intercepts. That sounds to me like it might be a horizontal asymptote, but let's check. For horizontal asymptotes, we check the degree of the numerator. The degree of the numerator is 0, and we check the degree of the denominator. That would be 2. When the degree of the numerator is less than the degree of the denominator, then y equals 0 is our horizontal asymptote. Probably still have a y-intercept, so let's plug in 0 to get our y-intercept. In this case, I think it might be easier to plug into the original instead of the reduced. Plugging in 0 gave me 1/2. So it looks like our y-intercept is 0, 1/2. Remember, intercepts are always written as a point. For rational functions, the way the symmetry works is that if you have two vertical asymptotes, you can have sort of the rational function, the positive rational function, then a cubic wave in between. Here you have the negative version of that. When your branches are both on the same side, so both above the horizontal asymptote or both below, then the little parabola sort of thing inside is going to be on the opposite side. So if these two branches are above, the parabola thing is below, and vice versa. And here would be your other option. Let's test out some values. I'm going to plug in -4 and 4. Interesting. So we ended up getting the same value, which means that your outer branches are both below the horizontal asymptote. So as you go toward infinity, the horizontal asymptote blocks you from going really up or down. And then as you go toward 0 in this case, or toward this vertical asymptote, we're going downward because we're not going to cross this horizontal asymptote in this place. Then this one will be the same because it's also below, which means that this point shows that we're going to have some sort of a parabolic looking feature inside. I'm going to plug in 1 just to give me an idea of where that goes, but honestly, if you just went like this, I would be fine with that. Plugging in 1 gets me 2/3. So this should be a little bit wider than it looked before. Now that we know the behavior as we're approaching those vertical asymptotes, let's go ahead and write them as limits. The limit of f of x as x approaches -2 from the left, okay, we're going down, so that's -infinity. The limit of f of x as x approaches -2 from the left, oh, we're going up, so we're going toward infinity. The limit of f of x as we approach +2 from the left, we're going upward, so that's +infinity. And the limit of f of x as x approaches +2 from the right, we're going down toward -infinity. Let's factor this one. We can factor this to be x minus 3x plus 4, x minus 3x plus 2, and this reduces, which gives us a whole at x equals whatever makes this equal to 0, so x equals 3. This reduces, so we also have a whole at 0, so we have 2 wholes, which leaves a much simpler looking reduced form. Your vertical asymptotes are anything that make the denominator equal to 0, so that would be -2. X-intercepts are anything that make the numerator equal to 0. So that would be -4, 0, and there's only one of those. Y-intercept is when you plug in 0 for x. And we get -2/3. So my domain is everything except the wholes and the vertical asymptotes. So x is a member of the set of all real numbers, but x cannot equal -2, 0, or 3. I will also write it in interval notation. Now I notice that these points are reflected, okay? They are the same distance from the intersection of the vertical and horizontal asymptotes. So I'm going to plug in -1, and that point should give me the y value for -3. That is a -1. So this goes down to -1. -1 is 2/3 away from the horizontal asymptote. So when we look at -3, our y value should be 2/3 away from our horizontal asymptote to give you that sort of reflection. If you just want to plug it in, that's fine too. And then our asymptotes really help guide us for the end behavior. Limits at our vertical asymptote, so the limit of f of x as x approaches -2 from the left, it's going upward into +infinity. But as we take the limit of f of x as x approaches -2 from the right, we are going down toward -infinity. We have that horizontal asymptote drawn. I want to also write it down. We found out that it is -1/3 coefficient over coefficient because the degrees are the same. So -1/3. There's a problem here though. We didn't graph our wholes, and you need to put those in. So when I graph my branches, I often put in the wholes later, but if you do that, you might forget to put them in, okay? So be sure to remind yourself somehow that you have to graph those wholes, and it has to be the very last thing that you do because you need to know what's happening to the curve around those wholes. So I've run into an issue here. I have a hole at the value x equals 0, but then I found a y-intercept. How is it a hole and an intercept? Well, it definitely can't be both a hole and an intercept. So you have to watch out when you do plug things into the reduced version. You have to remember what has already been taken out of the domain, what's already not allowed. So if you see the domain here does not allow 0, then you can't plug in 0, even to the reduced version. It's not going to, because if you plugged it into the original version, it would have given you undefined. So in this case, we have no y-intercept. And I hope that did not throw you off too much, but sometimes you'll have that, where you have a number that pops up as a whole and an intercept, or a whole and an asymptote. It can't be both, okay? So we have to make sure we've looked out for everything. So we do have a whole at 0, and we do have a whole at 3. Our curve continues toward this horizontal asymptote. So I'll put my whole here, and then a little further up when you get to 3. Remember to go back over those directions and make sure that you have written everything. Wholes, intercepts, horizontal, end behavior, asymptote, vertical asymptote, limit behavior, and domain, and sketching that graph. Our last problem, we're going to make sure to factor it first. So +3 and -1. And then once we take out that 2, we'll have x squared minus x minus 2, which will also factor. That becomes x minus 2, x plus 1, and nothing reduces. Nothing is going to reduce out of the original, so we have no wholes. Vertical asymptotes are whatever makes that denominator equal to 0, so x equals +2 and -1. After we have found our wholes and our vertical asymptotes, we automatically know the domain. The domain is everything except the wholes and the vertical asymptotes. So x is a member of the set of all real numbers, but x cannot equal 2 or -1, or in interval notation, it would be -infinity up until the first vertical asymptote, then vertical asymptote to vertical asymptote, then vertical asymptote to infinity. X-intercepts are zeros of the numerator, so x plus 3, so -3 would make that 0, +1 would make the other binomial 0, and then to get the y-intercept, we plug in 0, making sure that it is still a part of the domain before plugging it in, unlike last time. I ended up getting 3/4. 0, 3/4 is my y-intercept. And let's take a look at what our horizontal asymptote could be. We are concerned with the degree of the numerator and the denominator. The degrees are the same, so the leading coefficient of the numerator divided by the leading coefficient of the denominator is my horizontal asymptote. Y equals 1/2. Now, if you recall, there are only a certain number of options that a rational function, sort of the symmetry that a rational function can take when it has 2 vertical asymptotes. This middle section can either be sort of parabolic, going away from the 2 other branches, or it can sort of be a wave that passes by both branches. This crosses the horizontal asymptote in the middle, so I know that that is a wave. It looks like it's decreasing. That's my estimate. I'm going to test it out. It's okay for a graph to cross a horizontal asymptote. A horizontal asymptote is really what helps us know the end behavior. Outward though, further out, we will not be crossing horizontal asymptotes. So my estimate here is that this branch is in this lower left-hand corner, which would put this branch up here. I'm going to plug in 4. No, I'm going to plug in 4, because it's 2 units away from the vertical asymptote, and this point is also 2 units away from the vertical asymptote. I think my point is going to be here, but let's test it out. So plugging in 4 gave us 21 over 20, which is basically 1, which is what we had predicted before. So as you start to get a little bit more familiar or comfortable with rational functions, you can kind of see the patterns of symmetry that they have. Our last step is to write the limit notation of the vertical asymptote behavior. So that will be 4 statements, right? 2 per vertical asymptote. We want to say the limit of f of x as x approaches the first vertical asymptote, which is -1. From the left, we're going toward -infinity. But when we approach -1 from the right, we're going upward. That's positive infinity. When we approach the asymptote, the next one, 2 from the left, we are also going down, so -infinity. But the last one, as it approaches this asymptote from the right,